Quantum mechanics, note number 8, structure of the nucleus. Here we're going to look at how a nucleus in an atom is able to remain stable. We know that when we have a proton next to another proton, they want to repel. But how is it that protons can live beside other protons in the nucleus and actually stay stuck together? First off, let's call any particle in the nucleus a nucleon. So that includes protons and neutrons. So if we know protons want to repel from each other, there must be some sort of a glue. That glue ends up being the strong nuclear force. The strong nuclear force only acts on really small distances. In fact, it only acts on distances of about 10 to the negative 15 meters. 10 to the negative 15 ends up being 1 femtometer. So if we take a look at how the strong nuclear force results and how it compares to the electrostatic repulsion between the protons, we can make a chart of this. We can make a chart of force, where a positive value would be repulsive and negative value would be attractive, and compare it to distance apart, or radius. Here, let's say one proton is at the origin, and we're going to take another proton and slowly move it in closer to the other. First, we notice that they're going to repel, and that repulsion is going to grow and grow until about 2.5 femtometers. All of a sudden, they feel an attractive force towards each other. That's where the strong nuclear force kicks in. It only works on these small distances to try and keep those two protons in sort of a sweet spot, somewhere around just over 1 femtometer apart. Now this raises a larger question based on nuclear stability. If we look at all the atoms on the periodic table, we know that if we go from hydrogen and we go higher and higher, all the way up to uranium, which is the largest naturally occurring element, nucleuses get bigger and bigger and bigger. As nucleuses grow, they become unstable. In fact, anything larger than neon, special things have to start to happen to keep it stable. If we look at the nucleus, if the nucleus becomes larger than 2.5 femtometers, meaning its diameter is larger, the two edges of that nucleus are going to repel. What nature does is it ends up putting more neutrons into that nucleus so that they can exert the strong nuclear force and keep that nucleus together. So here we can make a plot, a stability chart, and compare the number of neutrons in each nucleus to the number of protons. What we notice is it's fairly linear up until 10, and then after 10 we get this scatter look to our chart. In that scattering portion, there are more neutrons in the rest of the elements than there are protons. We can add a line to this. This line stands for where protons equals neutrons. It's going to be a 45 degree. Any isotope below that line will be unstable. All naturally occurring elements should live above that line. If we look at the nucleus itself, we can look at something called nuclear binding energy. Nuclear binding energy is basically the energy needed to take one nucleon out of the nucleus. For example, if you want to take a nucleon, a neutron from helium, it's going to cost you 20 million electron volts. If you only remove an electron, that's only 13.6 electron volts. So it costs a lot of energy to actually take a nucleon out. So here, this will be our final plot. Let's look at each atom on the periodic table, and let's measure the binding energy per nucleon. This should tell us which nucleus is the most stable nucleus. The more energy it takes to take a nucleon out, that tells us the more stable that nucleus is. The first atom that we're going to add onto this is actually going to be uranium, the largest naturally occurring one. We're also going to notice that hydrogen is going to be on the other end. It's actually fairly easy to take a nucleon out of hydrogen. Helium is an increase from that. Lithium is next, but it's a decrease. If we were to plot the rest on, we would notice a pattern, but I'm going to reveal it to you now. There's an increase, a decrease, and then we see a curve between lithium and uranium. The top of this curve represents the most stable nucleus in the universe. In this case, it happens somewhere around number 26. This is the nucleus of iron. Because it's the most stable nucleus, it also means it's sort of in the lowest energy potential state. That means nucleuses that are larger want to break apart to get to this more energy efficient state. So when bigger nucleuses break apart, they undergo fission and release energy. Hydrogen wants to become like iron. It's actually going to fuse together with other stuff and release energy just to go to that more energy efficient state. So this is the difference between fusion and fission. There's also a mass defect we notice, and this comes from E equals mc squared. If we take a neutron from helium, we notice that if we measure the mass of the reactants and compare it to the mass of the products is slightly heavier. The energy we needed to take that neutron out actually turned itself into mass, creating this little bit of a mass defect.